In this case, what happens is that the test pattern generator and the response analyzer, so they are all integrated along with the chip. So, in this case, so no external test pattern is necessary. So, whatever test pattern needs to be applied, so they are generated on chip, and the response is also obtained, and it is analyzed on chip. So, that way it relieves the use of ATE, and particularly ATEs are going to be very costly. So, if we want to reduce the test cost, then this may be one approach, and in many cases it is possible, it is not possible to access the chip if it is say deep inside a system, or if it is a part of some environment where it is difficult to access the particular chip for test application, but at the same time it is very much necessary to test the chip periodically. So, in those situations, this built-in self-test philosophy, so that is going to help in the test generation process. So, to go back, so what are the problems in today's semiconductor testing? So, traditional test techniques become quite expensive. So, as we have seen, so it is the test pattern generation itself is a cumbersome process, and it requires a good algorithm to run, and it may require quite some time to generate the test patterns, and naturally application of those test patterns. And at the same time, as the complexity of the circuit is increasing, it is no longer provides sufficiently high fault coverage. So, if you try out with some random patterns, so you will not get good fault coverage. If you are trying out a dedicated test pattern generation algorithm, then also it is costly because of this test generation process, and of course, the test application is becoming another issue, like this automatic test equipment that we have. So, the cost of the system is going to be high with the increasing memory requirement and the number of pins that the ATE channel will have. So, that way it is going to be costly. So, we need some cheaper solution, and if we are trying to reduce the system cost. Why do we need built-in self-test? One special reason is that for mission critical applications. So, mission critical applications are those where we need to be sure about the correct operation of the system during the running of the application itself. So, many times we need to test the system again and again, particularly say when we have got medical applications. So, it is required that we check that medical appliances, so they are working properly. Similarly, when it is on some say critical operation, like say some cruise control type of application. So, there also we need to check the correctness of the system very often, and in that case, so if it is required to shut down the system and put it onto a test mode and then test it by applying some external pattern, so it become a cumbersome. Second important issue that we have is to detect unmodeled faults. Actually, as if we recollect, so what happens in a system is the occurrence of some defect, and when some defect occurs, so we actually try to detect those defects, but for our understanding, what we do is we model those defects as faults. Now, there may be many unmodeled defects which manifests as unmodeled faults. So, as the technologies are changing, so the newer fault models are necessary, as we have discussed previously, but it is not very easy to come up with comprehensive new fault models. So, that way the detection of unmodeled faults becomes an important issue, and the traditional test pattern generators, so they are targeted to a particular fault model, say staccato fault or bridging fault or delay fault, like that they are targeted to a particular fault model. So, the test pattern which are generated by them, so they are suitable for those fault models only. So, if there are some unmodeled faults, it is a bit unlikely that those test patterns will be able to detect those faults. So, this is another problem. Third problem is to provide remote diagnosis. As I was telling that many a times the system may not be accessible. So, it may be the environment may be such that it is not possible to access that system, but still we need to check the correctness of the system. So, for this type of application we need this remote diagnosis, and then this built-in self-test is going to help us, where the test pattern is generated in the circuit itself, and the responses are also analyzed in the along with the circuit. So, if we try to see the categories of this BIST, which is the full abbreviation of built-in self-test. So, they can be classified broadly into two categories, online BIST and offline BIST. So, online BIST means when the system is on, at that time it is going to test the system. So, it is testing is done concurrently with the when the system is on. So, again when the system is on, now there can be two situations. A system may be on, it may be working, doing its normal work, or it may be in an idle mode. Particularly say when we have got a pager for example. So, when it is doing the paging operation, so it is in the operational mode, but the pager when there is no message to be paged, so it remains idle. So, one possibility is that we extract those idle periods to do the testing of the pager. So, both are online, in both the cases the pager is on and it is operating, but in one case it is concurrent online testing where the system is operating, side by side we are extracting some information from the system and telling that we analyze that analyze the response and try to see what is whether the system is working properly or not. So, that is concurrent online BIST, and non-concurrent online BIST. So, they actually mean that we are looking into we are putting the system is in idle mode, and in the idle mode instead of applying say normal input. So, we are applying the test inputs, and those test inputs are actually being evaluated by the system, and the responses are getting compared. So, this is the online BIST. Now, there is offline BIST. So, in offline BIST we put the system in offline mode. So, it is not doing the work currently. So, it is put into a test mode, you can say, and then the test patterns are applied to the circuit and the responses are analyzed. So, at this when it is offline mode, so system is not doing its normal work. Okay. So, it is a normal work is suspended. Now, there can be two types of offline mode. One is functional offline BIST, and one is the structural offline BIST. So, functional offline BIST and the structural offline BIST, the major difference is that how do you generate how do you configure this BIST, or what type of patterns are used by the BIST. In functional offline BIST, so it is actually trying to test the system functionality. So, test patterns are generated keeping the system functionality in mind. So, it is actually doing a functional testing of the system. And another now a system may be viewed from two angle. One is the functional angle where it is talking about where we are talking about the system functionality. Another angle is the structural angle, which means that we are looking into how this system has been built, what are the components in this system. So, if you are looking from the structural angle, so you can have a BIST for the structural part. So, maybe my system has got 2-3 sub modules, and for each of those sub modules we can have they have got we know they are structures, and for testing those structures, so we apply some patterns. So, that is the structural BIST. So, based on the structure of the system and functional offline BIST. So, this is based on the function of the system. So, this is the classification. So, BIST can be classified into offline BIST and or online BIST. Again, the offline BIST can be classified into functional BIST or structural BIST. Online one can be classified in concurrent and non-concurrent. So, this classification was done by Abramovich in 1994. So, how does a typical logic BIST system look like? Okay. So, this is the circuit that we have, the circuit under test. Now, for in deterministic testing or ATPG based testing, what we had is, if this is the circuit under test, then from there was an equipment called ATE, automatic test equipment, and this automatic test equipment there was a memory which was holding the test patterns. Now, from the ATE, the test patterns were applied to this circuit under test, and the responses were obtained from this. So, these lines are known as ATE channels. They are called ATE channels. So, this was the situation. So, we apply the pattern that are stored in the memory. So, there is a controller which applies the patterns one after the other from the memory to this circuit under test, and the circuit under test returns the response, and this response is again compared with the golden response that is stored in the ATE. So, that was the situation for this external testing or this ATE based testing. In case of BIST, so we do not have any other ATE, but there is a test pattern generator which is integrated with the circuit, and there is an output response analyzer which is also integrated with the circuit. So, in deterministic case this TPG and ORA, so they were part of the ATE. Now, I do not have this TPG ORA separate, but they are part of the circuit itself. So, the advantage is that from outside world you just need to tell the system to start testing. So, there is no further requirement of transferring test patterns to the circuit or getting the responses and analyzing them. So, those requirements are not there. From outside world we can just give the command to start testing, and when it starts testing then after, so this response analyzer ultimately comes up with the answer yes or no. The system may be correct, system may be incorrect. So, there may be some fault. So, those are actually detected by the this response analyzer. So, there is a logic BIST controller which will tell the system like when to start testing, and maybe it needs to stop somewhere, or there may be some other controls that are needed. So, we will see when we go to these different types of BIST and all that. So, some other controls may be necessary, so which are provided by the logic BIST controller. So, this is a typical structure of a BIST system. BIST design rules, there are certain design rules that must be followed while having this logic BIST. So, it requires more stringent design restrictions when compared to conventional scan. Therefore, designing a logic BIST system, it is essential that the circuit under test meet all scan design rules and BIST specific design rules called BIST design rules. So, the scan design rules must be satisfied, because most of the cases in this this test from the test pattern generator. So, this generates bit streams to feed the scan chains of the circuit under test. So, whatever scan based rules we have, so they must be satisfied, and once apart from that some more rules are to be satisfied. So, the scan design rules we have seen previously. So, we have to look into these BIST specific design rules called or BIST design rules. So, a basic problem with this BIST based analysis is that there may be some x values, some unknown values or do not care values that may come, or so basically the unknown value. So, what happens is that in this case, so this response analyzer, so the test pattern generator is generating the patterns one after the other. So, they are applied to the circuit under test, and this response analyzer will try to will try to compact all those responses into some sort of a signature, and then finally it compares the signature with the golden signature. If the circuit is fault free, then due to application of the test pattern generated by the generator, so what is the response, and in the presence of some fault, what is the response. So, these two are compared. So, if it is faulty, then it will find out that okay, the signature is going to be different. Now, the problem is that if this if there are some sources of unknowns which that are there in this circuit under test, then this response analysis cannot be done properly, because the values during operation, so it may pick up any value 0 or 1. So, naturally we cannot consider it in the BIST session. So, what is required is that in for example, if we have got one unknown source x, okay, then one possibility is that in the BIST mode we make it 0. So, in BIST mode, so this is 1, so this is 0, so the AND gate output will be 0, whereas in the normal mode of operation this BIST mode input is 0. As a result, whatever be the value at this source, so it will come to this point. So, in this way, wherever we have got one unknown source x, so we put one inverter followed by AND gate, so that in BIST mode it will always result in a 0. So, this is called a 0 control point. So, 0 control point has to be maybe inserted into the circuit, so that these x's do not come in the circuit during BIST operation. Similarly, we can also have one control point. So, where we use instead of AND gate we use OR gate. So, this whatever be this x source in the BIST mode, this output is 1. So, this point is always 1. So, it is not an x. For normal operation, this BIST mode is 0. As a result, this whatever be the value at this source, it will come to the output of the into this signal line. So, there is no problem with the normal operation of the system. Sometimes another possibility is to use a bypass logic. So, in bypass logic what is done? So, maybe from primary input or some internal node the value is coming, and this x value is coming. So, in the BIST mode, so it will bypass this particular x value. So, BIST mode it will take the value from either primary input or some internal node which is not x. Okay. So, the circuit is slightly modified definitely, because now it is taking value from some internal node, not if not from primary input. So, in that case circuit is a bit modified, but the testing of the circuit can go on properly. And in the non BIST mode, this BIST mode control will be 0. As a result, this unknown source will come to the output. So, this line. So, normal operation is not hampered, but BIST mode it is taking some definite value. Then one possibility is that we can also put our D flip flop, and then through this scan chain. So, this flip flop is a part of the scan chain. Now, this through this scan chain, so we can put the desired value onto this. So, there may be a number of points at which we need to insert this different values in the BIST session. So, they can be put onto a scan chain, and through this scan chain, so we can put this value to a desired one. So, again this unknown source x is blocked by through this multiplexer and this D flip flop. Also, we can do it like this. So, here this is under this scan enable signal, this D input will come here. So, that is put into this flip flop, and now in the BIST mode. So, this Q value will be available through this multiplexer to the output. So, in normal operation this unknown source value comes here, and also this scan enable line will be 0. As a result, this x bit whatever be the unknown value, so that will come to the flip flop. So, if it is required that this the line x should be buffered. Okay, so, in this case it is getting buffered in the normal operation. So, scan enable is 0. So, it is coming to this flip flop, and then this BIST mode is also 0. So, it is through this flip flop it is going this scan input is coming to the output, the x input is coming to the output, whereas for normal scan operation, so it is getting buffered through this. So, that way we can insert one scan point. So, there are several x bounding methods that are going to be used. So, depending upon the nature of each unknown x source, several x bounding methods can be appropriate for use. Common problem, so increase the area of the design, because we are introducing some extra logic into the circuit, and also timing is getting affected, because if you look into this, so everywhere what we are doing is we are putting either extra AND gate, OR gate, multiplexer, or this flip flops. So, and flip flop and multiplexer. So, as a result, this delay of the circuit will change. Delay of the circuit, if they form a part of the critical path, then of course, the delay of the system will go up. So, timing is going to be affected. What are the unknown sources? So, we have said that if there is an unknown source, we bypass that unknown source by some mechanism. So, what are the unknown sources? First set of unknown sources are the analog blocks. Now, it is very much unlikely that a system will be completely digital, because it has to interact with the environment. So, there must be some analog components onto it also. So, this analog component values at the time of testing, so those values are not relevant. Okay. So, those, because we just want to have some typical value and try to see what is going to happen at the in the digital testing process. So, these analog block values are not meaningful. So, what we can do, these analog blocks, for the analog blocks we can add some bypass logic. So, this bypass logic addition is by this. So, if this is the analog block, so we bypass it by some other primary input or internal node value. So, that may be one possibility. We can add control only scan point. So, control only scan point is this one. So, this unknown source, so it is getting blocked by putting this value can be put through this D flip flop, and this so this can be done. Okay. Memories and non-scan storage elements. So, this is another source of unknown value. So, memory whatever value it will be initialized. So, it depends on the system operation. So, what is the content of memory, how is it going to change when the system is operating. So, that is totally dependent on the actual functionality of the system. So, memories are to be bypassed. Okay. So, because memory content is not known at it is not fixed at all the points, and the contents are also not known definitely. So, we have to bypass the memories that are there. And non-scan storage elements. So, scan storage we can put them on a scan chain and put some values there, but non-scan storage elements, so that they will create problems. So, what are the way outs? Way out is, one is bypass logic. So, we can put some bypass logic for them, and by that it can just bypass the content of memory or the non-scan storage elements, or we can initialize them to some proper values. So, that way what are the patterns that will come from them will be known. Sometimes we have combinational feedback loops. So, combinational feedback loops is another dangerous point, because whenever we are trying to do a fault simulation with this combinational feedback loops, so it is difficult to come up with the stable value. So, it is better that we insert we break that combinational feedback loop by putting some scan point. So, this scan point is this particular structure. So, we put some such structure, so that this the loop will be broken, and we can put the desired value onto this point via this D input and this flip flop, okay, in the scan mode. So, this can be done. Another difficulty that we have is with asynchronous set reset signals. So, asynchronous set reset signals, what happens is that in the functional mode, so this asynchronous set reset signal, if it is activated, the system will get reset. Now, during the BIST operation, if this reset signal comes, then that creates difficulty. So, somehow we have to stop that. So, what we can do, we can use this scan enable signal to protect each shift operation. So, basically this scan enable signal is 1, then this NOR gate output will be 0. As a result, this reset line will always get a 0. So, whatever be the set reset circuitry output, so it is not going to affect this flip flop. So, during the during the scan operation of this system, so this the flip flop will cannot get reset. So, basically this through this scanning line we are sending the data. So, and this scan enable line is 1. Whenever this scan enable is 1, this reset line will be 0. As a result, whatever be the operation of this set reset circuitry, this scan operation will go on smoothly. So, it will not reset the circuit. On the other hand, if you are going to check the operation of this set reset circuitry, then this SRCK line will make 1. As a result, we will get a 0 here. Then this scan enable line is also 0. So, so we will get a 1 at this point. So, whatever be the set reset circuitry, so that will get that will have effect on this flip flop. So, now we can check whether the circuit is getting reset by giving this SRCK signal. So, that is what is said, that using existing scan enable signal to protect each shift operation. So, shift operations are protected, so that they do not get reset by chance, and we add one set reset clock point on set reset signal to test the set reset circuitry. For there may be a number of such set reset points. So, we have to protect them individually, we have to check them, we test them individually. So, we whichever set reset circuitry we want to test, for that circuit we will make, for that input we will make the SRCK input 1. So, that that particular reset will only come. However, if this is say this SRCK is 0, so you will get a 1 at this point. So, you will get a 0. So, if we do not want that this set reset circuitry should affect the operation now, so we can make this SRCK line 0. So, if there are multiple SRCK lines, each one for each set reset circuitry, so we can test them separately. So, this is the operation, the timing operation that is shown. So, during the normal during this scan operation, when this scan enable signal is high, so this clock will be given for in the shifting operation, and then when this scan enable line is low, one capture signal may be given. So, that way this is doing the normal shift operation. And then when if we are interested to do a set reset check, then we can put this SRCK line high at some point of time, C2. If the C2 is high, then this scan enable is low, so the circuit will get reset. Then this of course in the shift window you will this line will remain low. So, you will be getting the whether the system has been reset or not, that can be tested. Another source of unknown is the tri-state bus. Like say this is the situation, one tri-state bus where there are two drivers D1 and D2 and there are two control signals EN1 and EN2 and it gets the value. Now, during normal operation of the system, so it is ensured that either of EN1 or EN2 they are activated. So, whenever we need the content of the bus, either EN1 or EN2 is activated. However, during test operation it is not it has to be guaranteed that exactly one of them is going to be 1, not both. So, this is modified by means of some one hot decoder. So, what is done? So, you see that if EN1 is 1, then this point will be 0 and as a result this will become as 0, and then if this scan enable is this scan enable is also 0, then this 0 will come here. As a result, this point will get 1 and this point will get a 0. So, you see that EN2, the EN1 being 1, EN1 being 1, so this signal is coming here, but so at that time this EN2 is 0, so it will be coming to this point. But suppose EN1 and EN2 both are 1, so in that case, so EN2 will come here. So, EN2 will this is an OR gate, so EN2 will be 1, but this point EN1 and EN2 both being 1, so this is 0. So, this is 0 and this scan enable signal, if it is there, then it is 1. So, this is 0. So, EN1 will not go in that case. So, this ensures that if both the enables are activated, only one of them will be through, okay. And if both are if one of them is 1, then the corresponding driver will be turned on. So, this is that is why it is called a one hot decoder. So, if both of them are 1, only one of them will finally survive, other one will die. So, this is required because there may be, so there may, when we are applying the test patterns, maybe EN1 and EN2 they become active simultaneously, but that may affect the system operation. So, this is the one hot decoding procedure.